Bismillahirrahmanirrahim. Welcome to digital communication course. Last time we have talked about digital modulation schemes. We actually had our first lecture of digital modulation schemes, and we have talked about two of the modulation schemes, namely pulse amplitude modulation and phase shift gain. We have talked about MRE PAM, MRE pulse amplitude modulation, which is a digital version of amplitude modulation, and we have also talked about MRE PSK, which is the digital modulation of phase modulation, digital version of phase modulation. For MRE PAM, we have seen its analytical expression last time. Let me recall it. We computed Sm of t as in generalized form as am subscript m under root 2 es divided by ts cos of 2 pi fct, right? And we defined am as 2 small m minus 1 minus capital M, where small m ranges from 1 till capital M, and capital M can be, say, 2, 4, 8. It is in the power of 2. Where k is the number of bits per symbol, right? So that's how we defined our analytical expression for pulse amplitude modulation, and we plotted it onto the constellation diagram, and we showed that we can easily compute the Euclidean distance between any two, say, pulse amplitude modulated signal classes. For example, if m is equal to 2, we have this scenario in which one of the signal class would come out to be, say, if you substitute m equal to 2 here, the a1 will come out to be 2 times 1 minus 2 will be minus under root es, and the other signal class will come out to be under root es, right? So assume you have capital M is equal to 2, then you will end up getting this constellation diagram, right? And the distance, Euclidean distance between them will come out to be d12 will come out to be 2 times under root es, right? So even if you increase this value of m, if you increase it and you substitute 4 here or 8 there, this distance between the two neighbors, it will remain the same, right? And that's why we call it the minimum distance. This distance will be d minimum. It will be equivalent to d minimum, right? So d minimum for amplitude shift gain or MRE PSK, they are both analogous names, right? The d minimum for it will come out to be same, and it will be equivalent to 2 times under root es, right? Similarly, we saw the analytical expression for MRE PSK, in which the generalized expression, the mth modulated signal, can be written easily using the basis functions as under root e cos of 2 pi by n small m minus 1 times phi 1 of t, that's the first basis function, minus under root e under root es sine of 2 pi by m small m minus 1 phi 2 of t, right, where phi 2 of t and phi 1 of t are the basis functions, right? So phi 1 of t and phi 2 of t have this expression 2 over ts cos 2 pi fct and under root 2 over ts sine 2 pi fct, right? So this was the generalized analytical form for FSK in terms of the basis functions. You can also express this analytical expression in terms of the basis function, which we did last time, and you can see your notes. We can also express it in terms of the basis function. Here we have expressed in terms of the basis function, right? All right. So again, if you, for example, substitute capital M is equivalent to 4, we end up getting a very nice constellation diagram in which 4 signals are plotted onto the constellation diagram using the two basis functions phi 1 and phi 2. Right? The energies come out to be under root ES each, right? If you measure this length, right, starting from origin till that point, it will be under root ES. Likewise for other signals, this is under root ES. Right, all the signals have equal energy. If you add more signals onto this digital communication system, for example m equivalent to 8, then you are going to insert 4 more points onto the constellation diagram, but all would have the same energy value along this radius of under root ES, right? Suppose this is the radius under root ES, and the FSK modulated signals will be placed on this circular region, right? For example, this is for m equivalent to 8. All these signals have equal energies, right, but different phase. We can also compute the Euclidean distance between any two signals or any pair of signals, for example S1 and S2 or S1 and S3 or S1 and S4, and we derived the generalized expression for the Euclidean distance between any two signals, right, which we will see shortly. The Km Euclidean distance between the kth signal class and mth signal class under Emery PSK scenario came out to be under root 2es 1 minus cos 2 pi by m minus k, right? That was the generalized expression. For example, if you substitute, if you take example for m equivalent to 4, say m is equivalent to 4, and if you construct the constellation diagram, you will end up getting such a constellation, right? And if you want to compute the distance between any two signals, right, say you would like to compute this distance, and this is say S1, and this is your signal class S2, S3 and S4. So it will be nothing but D12, which is 2Es 1 minus cos of 2 pi by 4. Say this is T2 minus 1, which is 1. By the way, and this is the absolute sign. You may substitute 1 minus 2 if k is greater than, say, if k is less than m, then you may substitute. If m is less than k, then you may substitute 1 minus 2 here and take the absolute of it, right? So the absolute sign will absorb the negative sign. So you will get 2Es 1 minus cos of pi by 2, right? Cos of 90 is 0, cos of pi by 2 is 0. So you will get the distance between signal class 1 and 2 as under root 2Es, right? And this is exactly the result if you compute the Euclidean distance between these two signal classes, given that signals are equal energy, right? And yes, the signals are equal energy. All of them are having Es energy, right? So that's how you compute the distance between the two signals in M-array FSK. If you recall, we also computed a similar analysis perhaps 3 or 4 lectures before, in which we computed the energy difference between any two signals, energy difference between any two signals as ED S1 of t minus S2 of t whole square dt, right? This was what we computed when we had, say, any two signals or any pair of signals, say S1 and S2, mentioned onto the constellation diagram. We can compute the energy difference between those two signals using this formula, right? I would like to basically prove that this D12 that we computed here using that formula is basically the same as actually if you take the square of this formula, you would exactly compute the ED. Basically, you are trying to compute the energy difference between the two signal points. Here you can see the norms of the energies are populated there, and if you take the difference between those two norms, you will end up getting the Euclidean distance, right? And if you square the Euclidean distance, you will compute the energy difference between the two signals, right? So I would like to prove here that this energy difference is basically the square of the Euclidean distance, right? So if you expand this expression there, this will be 0 till Ts S1 of t square plus 0 till Ts S2 of t square minus 2 times integral S1 of t S2 of t dt 0 till Ts, right? Now in our case, the two signals are orthogonal to each other, right? So this product will be, the integral of that product will be 0. Since if you integrate the two orthogonal signals and the answer, if they are different, the two orthogonal signals are different, the answer will come out to be 0. So as a result, we end up getting ES1 plus ES2, right? And if you say the two signals are equally likely, they have equal, the two signals are equally likely and equal energy signals, then you can write it as 2 times ES by saying that ES1 is equivalent to ES2 is equivalent to ES, right? So this will be your ED, and if you compare it with the result that we have just computed, the distance, Euclidean distance, that is the under root of this energy. So basically ED is the Euclidean distance square. Euclidean distance between the kth class and the mth class square will give you the energy difference between the kth class and the mth class, right? So we can compute the ED by just computing the Euclidean distance between the two signals and then taking its square, right? That was one important result. I wanted to relate it the two way, basically the Euclidean distance and the energy difference. Now let's move a little ahead and talk about the another modulation scheme, which is FSK. And by the way, you should recall that we have expressed our probability of error equation in terms of the energy difference ED, right? So if I substitute Euclidean distance instead of ED, so I can get the probability of error expression in terms of Euclidean distance between two signal classes, right? And that is very convenient, and I will tell you shortly in this lecture that we are going to use that expression when we are going to compute, when we are going to approximate the probability of error for the larger sizes of the signal classes, right? Under that context, we would be interested to find out the Euclidean distances between the two signals, and would like to express the probability of error expression in terms of the Euclidean distances between the two signals, right? So let's move ahead and let's talk about the FSK, the last modulation scheme, which is frequency shift keying. And again, we will follow the same route, and we will first write down the generalized expression for M-array FSK scheme, M-array frequency shift keying. Sm of t be the mth modulated signal is real of 2Es by Ts, which is the amplitude of the carrier represented in terms of energy and the symbol time, e raised to power j 2 pi delta f m minus 1 t times e raised to power j 2 pi fc t. I'll explain you shortly what does this mean, this exponential. This basically is the frequency which is dependent on the message index m, and that frequency portion is added onto the carrier frequency fc, right? So if you combine the two exponentials, you will get real of 2es over ts e raised to power j 2 pi fc plus m minus 1 times delta f t. You see, the basic concept of FM or frequency modulation is that the frequency of the carrier is going to vary with respect to the message signal, right? The carrier frequency of the carrier should proportionally vary with the message signal, right? That is the basic concept of frequency modulation. So somehow we need to embed the message signals information into the carrier signals frequency, right? So we all know, and if you recall the last lecture, we have talked about this index M, the small index M. What is it? This is basically representing the message signal, the unique message signal representation. If you recall the table, for example, if you construct a similar table for FSK in which we have, say, the column for M, and there's one column for the frequency content FC plus M minus 1 times delta F, right? And here we have another column for symbol, right? And here we have, say, column for the bit, right? So assume we have capital M is equivalent to 4 as an example. We are going to get 4 unique bit patterns, 0 0 1 0 0 1 and 1 1, right? And correspondingly we will have symbol 1, symbol 2, symbol 3, symbol 4. These are the 4 message symbols that can be generated out of these random bits, right? And this index is M, which is representing each message pattern uniquely, right? Each bit pattern is represented uniquely by this index M, right? So for example, if you have a random 10 bit to be sent from transmitter N, you would be basically associating that pattern with the index 2, right? Message index 2 would be selected if you have 10 to be sent from transmitter N. But since we are doing frequency shift keying or frequency modulation, we need to embed this information into the frequency of the carrier. And this column is for the frequency calculation for the carrier. That is, what frequency of your carrier is going to be calculated against that particular index M. So for example, if your index M is 1, right? And if your carrier frequency, the center frequency is, say, FC, you will get FC plus 1 minus 1 is 0 times delta F equivalent to FC as the carrier frequency. Whenever you have bit pattern 0 0 to be sent from transmitter N, you are going to choose the carrier frequency with the frequency FC from the transmitter end, right? So whenever you have a bit pattern, say 10 to be sent from transmitter end, you will calculate FC plus 2 minus 1 is 1, which is again delta F. In other words, then you would be sending the carrier of frequency FC plus delta F, right? Some different frequency than the previous one, offset by delta F amount, right? And likewise for the message pattern M3 and M4, FC plus 2 times delta F and FC plus 3 times delta F. Now you see, whenever you have 0 0 to be sent from transmitter end, you are going to send the carrier with frequency FC. And whenever you have, say, 1 1 to be sent from transmitter end, you are going to send carrier with frequency FC plus 3 delta F, right? So frequency of the carrier term is going to vary with respect to the information bit, right? That's the idea behind frequency shift keying. All right. Now let's see what is delta F, right? Delta F is apparently it is nothing but the difference between the two frequencies. If you two neighbor frequencies, right? If you subtract the two carrier frequencies here, if you see here, the difference is exactly delta F. And if you subtract these two, again the difference is delta F. If you subtract these two, again the difference will come out to be delta F. So delta F is the difference where the delta F is the difference between the mth frequency carrier and its neighbor, say F of subscript M minus 1, right? Where FM, F subscript M, can be written as FC plus M minus 1 delta F, right? This Fm is the carrier frequency, right? And it depends on the index M and the spacing between the two frequencies, two neighbor frequencies, delta F, right? So that's the idea of frequency shift keying, and it's a very simple idea. We would like to embed the information onto the frequency of the carrier. The amplitude remains constant. The phase has nothing to do with it. Only the frequency varies with respect to the index M. And this index M is dependent on the bits, how you have designed your transmitter, whether you have M equivalent to 4, that is 4 symbols to be sent, or M equivalent to 2. If M is equivalent to 2, then you would only have binary data bits like 1 or 0, 2 symbols max, right? And correspondingly 2 index of M, that is 1 and 2, and therefore only 2 frequencies, either FC or FC plus delta F, right? For M equivalent to 8, you would have 8 frequencies, right? So whenever M increases, the requirement on the number of carrier frequencies from the transmitter end, it increases, right? Vice versa. In other words, bandwidth increases. So if you want to pack more bits into the symbols, you will have to use more frequencies, and therefore you would have to use more bandwidth to accommodate those symbols and high data rate, right? Now suppose you have M equivalent to 4 as an example, in which you would require to have 4 carrier frequencies to be selected depending upon the bits that you would like to send. Now assume you have FC equivalent to say 1 megahertz and delta F as say 1 kilohertz, right? So whenever you would be sending 00 from the transmitter end, the carrier frequency would be chosen as 1 megahertz, right? 1 megahertz frequency carrier. Whenever you have 10 to be sent, your frequency will be FC plus 1 kilohertz, which is 1.1 megahertz, right? And likewise for the other possible message signals, 1.2 megahertz and 1.3 megahertz, right? So suppose you have the binary data in this form out of the sampler, right? You are going to pair up the 2 bits each to form a symbol. 10 corresponds to symbol S2, let's say S2 here. Then 11 corresponds to the symbol S4, S4 there. 01 corresponds to the symbol S3, again S3, and again S3 here, and say this is your 00, say S1, and this is your 11, say S4, right? So now you have done the bit to symbol mapping, and now the next task would be to modulate it using FSK. And given this theory, the carriers that you would like to generate out of this data, you would like to have 1.1 megahertz frequency carrier for symbol S2, and whenever you are going to send symbol S4, you would have to choose the carrier frequency of 1.3 megahertz, and for symbol 3 you have 1.2 megahertz. And if you plot it onto the frequency axis, you would see that you would have spikes on either 1 megahertz, 1.1 megahertz, 1.2 megahertz, and 1.3 megahertz, right? And this range will be called as your passband bandwidth. Now you see the bandwidth increases as you have higher number of symbols to be sent from the transmitter end. So if you have only 2 symbols to be sent, say M equivalent to 2 versus M equivalent to 4, if you compare the 2 scenarios, for M equivalent to 2 you would have only 2 frequencies, right? And for the same spacing between the two, if you keep the spacing between the two signals fixed, m equivalent to 2 will have smaller bandwidth requirement compared to m equivalent to 4, right? This is important since in FSK, the main concern is the bandwidth. The bandwidth increases with the message signals. With the possibilities of the message signals, the bandwidth increases. Because for each unique possibility of the message signal, you would have to use a different unique frequency so that you can, at the receiver end, recognize that frequency and therefore decode that message signal out of it. It also depends on the choice of delta F, that is carrier frequency spacing between the two frequency carriers, that how much of it that you are going to have in your system design. Say for example, delta F is very high. If delta F is high, then you would have higher bandwidth requirement, right? Bandwidth requirement would be high. And if delta F is small, the spacing between the two carriers will be small and the bandwidth occupied by the whole communication system will be small, right? So delta F generally for orthogonal frequencies and for coherent reception is determined as 1 over 2 times TS. That is the minimum delta F or minimum carrier frequency spacing that you can have that generates orthogonal frequencies. The frequencies would be orthogonal to each other if you generate delta F like that. And the reception of those signals at the receiver end has to be coherent. That is, you have to generate the same frequency at the receiver end in order to decode the modulated signals. So under that scenario, the delta F is required to be computed as 1 over 2 times TS. And if you can have a non-coherent receiver at the receiver end, then you may choose delta F as 1 over TS. This will be the minimum delta F required, or you can have for a non-coherent reception of the FSK signals, right? The proof of these two claims is there in the book, which I will not cover in this course due to short of time. I have skipped that proof. It will require another lecture or two to understand this. All right, welcome to the second session of the digital communication lecture. In this session, we are going to talk about the union bounds on probability of error for the digital modulation schemes. It is generally true, the bounds are generally true for larger values of signal class M. That is generally true for M greater and equivalent to 4, in which you have larger number of signals to be sent from transmitter end. Right, so let's have the background of it and develop the background for it, and then we will derive the probability of error expressions for the 3 different modulation schemes that we have studied shortly. All right, so recall the optimum detector block diagram. If you recall it, we have received signal at the receiver end, which passes through a number of blocks. Assume we have the optimum correlator implementation at the receiver end. Match filter based, or say correlator based implementation, then you would have several different correlators placed depending upon the number of basis functions that you have, right? And then you would like to integrate it right, something like that. And then in the end you compute this summation I is equivalent to 1 to n RISKI, right? And you also add you compensate basically for the unequal energy and unequally likely probabilities, right? You compensate for it by adding the amounts, the required amounts, after you compute this summation and before you take the decisions in the decision block here. Decision block or comparator, right? Here you have, say, B1, B2 up till BK, and what you are adding here is AKs, A1, A2 being added, and then A3 being added, and AK being added here, where BK was n naught by 2 natural log of probability of signal class SK minus the energies, right? Kth signal energy plus R times SK, right? This was your BK, that is the last point before you take the decision, right? And this, the two expressions here were AKs, were denoted by this variable AK. So you have BK, another variable BK, just before you take the decision, right? You have this variable BK, which is equivalent to AK plus whatever you had here in the block diagram, which is nothing but R transpose times SK. All these are vectors. R is a vector and SK is a vector. All right. So that was what we talked about when we had a discussion on optimum receivers, and here we have written the same block diagram for reference. We are going to start from here and build our analysis for probability of error using this block diagram. All right. So now let's talk about probability of error, and if I use this portion, probability of error, let me write down here before I move to the next. Probability of error given the signal class SK is equivalent to probability of union of all such events when BK is less than BJ for J not equivalent to K. Assume you send the signal class as K, right? And one of the branches, say B2, comes out to be the highest among all the other branches, right? So the decision block will take the decision in favor of the signal class S2, whereas you sent the signal class SK. So therefore, that particular decision would be the erroneous decision, right? And it will contribute towards the error. Likewise, if you take the decision in favor of any other signal class other than BK, you would again be taking a wrong decision, right? So if you accumulate all such error events, you can put it here in this form, analytical form. That is the union of all such events when you took a decision in favor of jth signal class, right? So since you know from probability theory that probability of union of the two events A union B is equivalent to probability of A plus probability of B minus probability of A intersection B, right? We can apply the same formula in our problem, since we also have the union of all the error events we can use and apply this probability formula in our problem, and we can write it down as probability of error given Sk less than and equivalent to summation of all the error events from j1 to m and j not equivalent to k, probability of bk less than bj given signal class sk sent, right? So this summation is basically analogous to as if you are adding the events, right? Probability of A and probability of B. So the summation is the summation of all such error events. This third term, in which you compute the intersection of the two events, is generally difficult to compute here for our probability analysis. So we don't include it here in the equation, and we have inserted less than sign for this particular reason, right? Otherwise, we would have inserted equal to sign here, and we would have subtracted the third term as required in the probability equation, right? So we haven't included the third term here in our analysis, and we have included the less than sign to compensate for it. This is generally difficult to compute for our probability of error analysis. That's why we say we have approximation towards the actual probability value. We don't have the exact probability of error computed out of this analysis, right? So in the next slide, we see how we can further solve this problem and further substitute it in terms of the Q functions for different digital modulation schemes. All right. Right. Probability of error given Sk, I am repeating the same equation here again. J equivalent to 1, J not equivalent to K, and it goes till capital M. Probability of Bk less than Bj given the signal class Sk sent. Let's compute the total probability of error, total average error probability. Total probability of error using the same formula as we used in the previous examples, in the previous lectures. We have probability of error equivalent to summation from k equivalent to 1 till the mth signal class, probability of error given Sk times probability of Sk, right? If you substitute this here in this equation, you get probability of error less than and equivalent to summation k is equivalent to 1 till capital M. That's the outer summation, and then the inner summation from that expression comes out to be j equivalent to 1 till j not equivalent to k and goes till M. Probability of Bk less than Bj given the signal class Sk times this value, probability of Sk, right? Now, if you assume equally likely signals, say assume you have signals that have equally likely probabilities, this probability of Sk will be equivalent to some constant value, which is 1 over the total number of signal classes, which is M. So probability of Sk for equally likely signals, probability of Sk will be equivalent to one over M, right? So if you have two signal classes, then the probability of symbol class 1 would be equivalent to probability of symbol class 2, and that result would be equivalent to 1 over 2, right? So for equally likely, this is assumed to be constant. It will be taken out of the summation, and we can write down probability of error as 1 over m summation, repeating basically the same expression that we have written above, not equivalent to k till m probability of bk less than bj given signal class sk, right? Now let's see what are these probabilities. Since we have to represent this in terms of Q function, we would like to analyze this. What is this? So let's see and expand it for different values of k and j. So for example, assume k is equivalent to 1, right? Then j will start from 2 till capital M. J cannot be 1, right? Since the summation here has a condition that j cannot be equivalent to k. So if k is chosen as 1, so j cannot start from 1. It will start from 2, right? And it will go till capital M, right? So as a result, we get these probabilities. Probability that B1 less than B2 given signal class S1 send, and similarly we get B1 less than B3 given signal class S1 send till probability that B1 is less than Bm given signal class S1 send, right? And therefore these all are pairwise probabilities. What we see here, these are pairwise probabilities, that is the comparison between the two signal classes, either 1 or 3 and 1 or 2 or 1 or capital M. All these are pairwise error probabilities, right? Likewise, if you substitute k is equivalent to 2, then the pair changes, and you compute probability of B2 less than B1 given signal class S2 sent. Similarly, probability of B2 less than B3. You can't choose 2 here, right? Since j cannot be equivalent to k. Here k was true, so j cannot be equivalent to 2, right? So after you have computed this pair probability, you cannot go for B2 here. You can only substitute B3 or higher till Bm given the signal class S2 send, till probability of B2 less than Bm given signal class S2. And likewise you do for all other classes and substitute k till capital M and come up with the expressions for all the pairwise error probabilities, right? Now for pairwise error probabilities, we have already seen the expression in terms of Q function. If you recall 3 or 4 lectures back, we expressed the pairwise error probability, pairwise error probability is expressed as Q of under root E, Q of under root ED divided by 2N naught. Reference to this is mentioned in the one of the lectures in which we started probability of error analysis, and we computed the error probability for a pair for two signals, basically, that is a pair of a signal, in terms of the energy difference, right? And this ED is the energy difference between the pair. And in today's lecture, I have told you this ED is nothing but, since ED is equivalent to dkj square, that is, if you compute the Euclidean distance between the kth signal class and the jth signal class, and if you square it, you will end up getting the energy difference between the two, right? So you can express this Q function in terms of the Euclidean distance between the two signals in the pair, right? So in the next step, we are going to substitute dkj here in this expression, and we will see that we can actually substitute these pairwise error probabilities in terms of the Q function and the Euclidean distance between the signal classes under consideration. Now, since we have these pairs, each pair can be represented in terms of this probability, right? For example, if I ask you the probability of error against this expression, this can be written as Q function of under root E 1,3, or in other words, D 1,3 square divided by 2N naught, right? And likewise for all other probability of error pairs, you can have the pairwise probability of error expression for all these, right? And here in this summation, you have to accumulate all such pairs to come up with the total error probability, right? And this is exactly what we are going to do in the next step. All right. So let's write down the pairwise error probabilities. Let me first write down the expression again here, and then we will substitute the pairwise error probability. Bk less than bj given the signal class sk set. So all these are pairwise error probabilities. Pairwise error probabilities. So in terms of pairwise error probabilities, this can be written as 1/m probability of error k1 to m. J goes from 1 till capital M, and j cannot be equivalent to k. Q of under root dkj square divided by 2N naught, right? Here is the simplified expression for the approximation of probability of error. This is the generalized expression. I haven't talked about the specific modulation scheme as of yet. For general expression, this is what you are going to use, and you may call it generalized approximation probability of error approximation for equally likely signals. Why? Because we have substituted 1 over m here, and this is there because of the equally likely condition. If we have unequally likely signals, then probability of SK would be multiplied and it would be placed under the summation, right? So for equally likely signals, this is the generalized expression for the probability. Now assume the signals are orthogonal in nature. Let's assume it for frequency shift keying, because we can assume orthogonal signals in frequency shift keying. So assume we have M array orthogonal frequency shift keying. That is one modulation signal type, right? Digital modulation or frequency modulation. Then all pairwise error probabilities will become the same. This is very important, how it is going to become the same. Let's see how. This is the pairwise error probability expression, right, for any signal class. If you assume the signals are orthogonal in nature, then, and let's say if you plot it on constellation diagram given m equivalent to 2, one of the signal will be here, the other one will be there, right? And this would be the energy difference ED between the two pairs, right? Signal class S1 and S2, right? And if you have, say, m equivalent to 3, hypothetically speaking, if you have 3 signals, then you would need another dimension to represent that signal. Why? Because you can't have one frequency represented in terms of the other. You would have to have another basis function to represent the third frequency. So you need to have another dimension, third dimension, to represent the third signal point, and that would be orthogonal to the first 2 points, right? In that case, if you compute the energy difference between the third point and the first one, or the second point and the third one, you will again get the same energy ED, right? The energy difference will not change when you increase the dimensions in the constellation diagram. The difference energy will be the same. And since we are talking about orthogonal signals, M-array orthogonal FSK, the signals will have equal energy difference if you compute it onto the constellation diagram. I'm unable to visualize 3 dimensions here, or even 4 dimensions. It would be very difficult. I can only visualize it on 2-dimension plane, and I can show you, like I've shown you here, that the ED between the 2 signals. This will remain same if you increase the number of signals and put it on the constellation diagram somehow. The ED will remain the same. Now, if ED is fixed, or it remains the same irrespective of the value of capital M, then this Q function can be taken out of the summation, right? Now, since this Q function will have a fixed value, irrespective of the value of capital M. So whether you vary K or J, whatever the values of K and J will be, whatever the pair is, this Q function will be fixed and would be equivalent to this value for orthogonal signal classes. Remember, we computed this result. For orthogonal frequencies, we have computed it, and it comes out to be this expression, right? I guess ES over N naught, I guess so. Yes. 2ES, 2 times ES, and then the 2 gets cancelled with the denominator, and you end up getting 2ES being cancelled with the 2 in the denominator, and you end up getting this expression for orthogonals. So for orthogonal signaling, this is the case, and we substitute probability of error as 1 over m q of under root es divided by n naught summation k goes from 1 till capital M, j goes from 1 till capital M, j not equivalent to k, and you're integrating it on 1, constant 1, right? Now this summation, the two summations, if you expand it, you will get m number here. If you expand summation, the first summation, you'll get m, and from the next summation you'll get capital M minus 1, right? This is from basic maths. If you expand this summation, assuming j not equivalent to k, you will end up getting m terms minus one of the terms, minus 1, m minus 1. So in short, probability of error for orthogonal signaling is even more simplified form as 1 over m times m minus 1 q of under root es over n naught, right? This m in the denominator gets cancelled with the m in the numerator, and you end up getting n minus 1 times q of under root es. This is valid for orthogonal signaling, or in other words, we have just computed the generalized expression for M-ary orthogonal FSK and equally likely with equally likely signals, right? Next, we are going to have a few examples for different modulation schemes other than FSK, and using the constellation diagram, we would like to compute these Euclidean distances, and we would like to substitute those distances there in the expression, and hence we would be approximating the total average error probability for various modulation schemes and their corresponding constellation diagrams, and for their corresponding constellation diagrams, right? Thank you.